Welcome to Mathematical Structure for Computer Science, CS 113, also known as Discrete Mathematics. So in this lectures, we're going to discuss about discrete probability. That's introduction to discrete probabilities. In this course, we are not going to discuss about normal distribution or normal probability distribution. We are only going to focus on only the discrete probabilities. As we know in probabilities, we have the two major distributions. A discrete distribution, the random variable is based on counting. Normal distribution, the random variable is based on measurement. And in this course, which is again discrete mathematics, we are going to focus on only discrete probabilities. So this course covers our course textbook, chapter 7, section 7.1, which is Introduction to Discrete Probabilities. Our main objective is to focus on finite probabilities and also probabilities of complements and union of events. This is one of the theories of probabilities. And also we're going to discuss about probabilistic reasoning. So we start with the probability of an event. Here we are going to focus on Perry-Simon-Laplace definition or classical theory. So we're first going to study the Perry-Simon-Laplace's classical theory of probability, which was introduced in the 18th century. And he analyzed a games of a chance. So this is the definition. We first define these key terms. What is an experiment? What is a sample space? And what is an event? So an experiment is a procedure that yields one of a given set of possible outcomes. In a research field, we can say an experiment is a scientific process of trying to find a result, but we are going to follow a scientific principles based on how we are going to set our lab or set our experiment design process, such as how do we collect our data, what subjects are we using for the studies. Here we said an experiment again is a procedure. This procedure must be a scientific procedure or must follow some scientific principles that will yield one of the given set of possible outcomes. And also a sample space of the experiment is the set of all the possible outcomes. So an example, if we have an experiment that we want to toss a coin, we know that when we toss a coin, we only have two possible outcomes. Either we get the tail or we get the head. So the sample space will be both the head and tail. So again, a sample space of an experiment is the set of all the possible outcomes in the experiment. So in this case, tossing a coin will be our experiment. Also, an event is the subset of the sample space. So when I toss my coin and I get a tail will be an event. What is the probability of getting a tail? Or what is the probability of getting a head? That will be my event. In this case, I'm tossing a coin. A coin have only two possible outcomes. So randomly, in a fair chance, we will say that the probability of getting a tail or a head is 50% or 0.5. So again, this is the beginning of our introduction to probabilities. And the first three key terms here is what we are going to focus a lot in this section. So we should know what is an experiment. Again, a procedure that will yield one of the given set of possible outcomes. And a sample space of the experiment is all the possible outcome of the experiment. And an event will be the subset of a sample space. So again, the example we gave was tossing a coin, which is an experiment. The sample space will be both head and tail. We have only two possible outcomes. Event can be having only a tail or having only a head. So we can see that the event will be the subset of a sample space. So here's how Laplace defined the probability of an event. And this is his definition. Here we say if S is a finite sample space of equally likely outcome. So here we have a fair experiment, a fair outcome. Again, if S is a finite sample space, which is again the possible outcomes or the possible outcome of an experiment. And here we say it's of equal likely outcome. So tossing the coin, equal likely outcome means we have a probability of what? Head will be 0.5, tail also will be 0.5. They all have equal likely outcome. And also we have a E, which is an event that is a subset of S. Then the probability of event is E divided by S. So the probability of event, it will be the possible E divided by the possible S. Again, S is what? The subset of a sample space. And then E is our event, probability of event. And that's what we are looking for. So probability of event will be, again, the E divided by S. Now, for every event E, we're always going to have a probability of E, which will be between 0 to 1. So if probability of E, or let's say probability of an event is 0, it means we are 100% sure that event will never take place. Now, if the probability of E or event is 1, then we are 100% sure the outcome will take place or the event will take place. So again, the example of a probability of a head and tail, if we say it's equally, then most likely the probability of getting a head will be 50%. Why? Because the possible outcome S is 2. The event is only 1, so it will be E1 divided by 2. Again, E will be the possible events. Here we have only probability of a head, so the event is 1. And then the sample space for when we toss a coin is only 2, head or tail. So probability of getting head will be 1/2, which is 0.5. And this is one of the first rule of probability. Probability of any event, always the answer will be between 0 to 1. So this follows directly from the definition because we say what? Probability of A should be either equal to 0 or greater. And it should be between that 0 all the way to either less than or equal to 1. So the value always, a probability of any event will always be between 0 and 1. And that was, again, the definition of Laplace probability concept. So we have a good example here now. Here, the example here says if we have an urn which contains 4 blue balls and also 5 red balls. What is the probability that a ball chosen from the horn is blue? Now, when we look at this question, in this case, we are using the simple Laplace theory or definition. How many balls we have for blue? We have 4. How many balls we have for red? We have 5. That means the total balls in the horn is 9, 5 and 4. And what is the probability of choosing blue? So this means probability of an event of getting blue ball. It will be how many blue balls we have divided by total blue ball. Total balls in the horn. So it will be 4/9. So here we say the probability that the ball is chosen is 4/9. Why? Because we have 4 blue balls. And what is the probability of getting blue ball? Is the total blue balls we have divided by total all the balls we have. Here we have only blue and red. So total of blue and red is 9. So it's 4 by 9. Here we say since there are 9 possible outcomes, and also the 4 of these outcomes is blue ball, it will be 4 by 9. So next example, what is the probability that when 2 dice are rolled, the sum of the numbers on the 2 dice is 7? So here we have to know first the sample space, which is all the possible outcomes when we threw 2 dice. Then we see, for example, when I threw a die, 2 dice, there's one outcome that can be 1, 1. So 1 plus 1 is 2. There's one can be 1, 2, 3, 3, 1, 4, 1, etc. But our goal is the sum of 7. Okay, so the sum of 7 means 1 and 6 will give me 7, 2 and 5 will give me 7, 3 and 4 will give me 7, and then 5 and 2, we already have 2 and 5. So those are 2 and 5 and 5 and 2 is the same. So we have to count the number of possible outcome when we threw the 2 dice, we will get total 7. Then we divide it by all the possible outcome. This including even if I threw it, the minimum if I threw 2 dice will be 1. I mean 1 and 1, so that will be 2. So we can have 2, we can have 3, we can have 4, all the way to 12 because we can have 6, 6. We cannot have 13 because there's no 8 and 5. The maximum we can go is 12. So we have to know again the outcome. So that's what we said here. By the product rule, as we said earlier, we are throwing 2 dice. And the highest value is 6, from 1 to 6. So by product rule, there are 6 square. That means we have a possible of 36 outcome. Because one die will give me from 1 to 6. Second die will give me from 1 to 6. When we join the 2 combinations together, all possible outcome will be 6 times 6. So that will give me 36. Now, if I have 3 dice, then it will be 6 times 6 times 6, because each have possible 6 outcome, 1 to 6, 1 to 6. So if we know this, now we want to know how many times if we threw the 2 dice, we get a total of 7. Here, we do the combination, we saw we have 6. 6 of this sum is to 7. And this is very straightforward. We can start with 1 and 5 is 7. So we start with 1 and 6. 1 and 6 is 1, then 2 and 5, then 3 and 4, and then we keep going. So the total will give us possible 7. Together, here we are doing the sum of 6. Let's see the question again. 2 dice roll, the sum of the numbers on the 2 dice is 7. So yes, 7. So this means we have 6 of this possible. As I said, 1, 6, 2, 5, 3, 4. Then we keep going, we get possible 6. So this means we have 6 divided by 36. So the probability that if I threw the 2 dice, I will get a total of 7 will be 1/6. So we're going to apply another example here using the Laplace definition. Here we have a lottery. So in a lottery, a player wins a large prize when they pick 4 digits that match in correct order, 4 digits selected by random mechanical process. What is the probability that a player wins the prize? So here, first of all, we have to know the number of possible digits. Here we are talking about regular English mathematics digits, decimal number system. So it will be 10. So we have possible 10 digits. So by product rule, we are trying to randomly select 4 digits. So the possible outcome of any possible 4 digits It's same as the previous example. I have a dice, and the dice, I know we have possible 6 digits because from 1 to 6 digits. Now, if I have 2 dice, the possible outcome of combinations all together will be 6 times 6. If I have 3 dice, it will be 6 times 6 times 6. Here we are talking about digits. We have from 0 to 9, which is 10 digits. In this lottery, we have to select 4 digits to win if it matches. So what is the possible outcome? It will be 10 times 10 times 10 times 10, 4 times, because when I pick 1 digit, I have a possible of 10. If I pick 10, another 1 digit, a possible of 10. Unless we have a rule saying that after we pick a digit, 1 digit, we cannot pick that digit no more. So which means the lottery winning game will be a unique 4-digit numbers. In that case, then it will be 9, 8, 7, and 10. First, I have 10 possible digits. When I pick 1, it's only 9 left. So 10 times 9. When I pick another one, only 8 left. So times 8. When I pick another one, only 7. So it will be 10 times 9 times 8 times 7. This is if we want to win. The rule said we need to have 4 unique numbers. We can't repeat the same number. But in this question, I can pick 4444 or 7771. And it can be a winning number. So which means we can get the same digit more than once. So that means we're going to have 10 times 10 times 10 times 10, 4 times, which will give us 10,000. So this is the 10,000 ways to pick the 4 digits. Now we say that now this means this is the possible combination of 4 digits we can get from the 10, to pick 4 digits from the 10 without replacement. But only 1 digit will win. So that means the probability that I will win a game, it will be 1 divided by 10,000. So here we say that since there's only 1 way to pick the correct digits, only 1 4-digit number will win out of the 10,000. So the probability of winning the large prize is 1 divided by 10,000, which will give us 0.0001. Again, let's go through the question one more time. Here, the question said, we have a lottery, and the player wins the large prize when they pick the 4 digits that match in correct order. 4 digits selected by random mechanical process. What is the probability that the player wins the prize? Now, this question didn't tell us that the 4 digits must be unique. I mean, we can't repeat the same digit more than once. So if that's the case, the chance of me picking 1 digit out of 10 is 10. The chance of picking 2nd digit, repeating it twice, then it will be 10 times 10, 100. The chance of picking the 3rd digit, repeating 10 digits 3 times to get 3 digits, it will be 10 times 10 times 10, and the 4th times 10. So that gives us the 10,000. Now, if the question said we should pick 5 correct digits, then it will be 10 to the power 5, which will give us 100,000. So the 10,000 here is what we call the sample space, the possible outcome, the possible 4-digit outcome altogether. But we need only 1 can win, only 1 4 set numbers will win. So the probability of winning will be 1 divided by 10,000. And here we say that the smaller prize is won if only 3 digits are matched. What is the probability that the player wins the small prize? Okay, so this probability will reduce. I mean, it will get higher. See, the probability of this was only 0.0001, which is very low. But now, if it's 3 digits, it will get a little bit higher. So what will be the answer here? We say the solution is if exactly 3 3 digits are matched, one of the 4 digits must be incorrect and the other 3 digits must be correct. So for the digit that is incorrect, we have 9 possible choices. Which is incorrect, we have 9 possible choices. Hence, by the sum rule, there's a total of 36 possible ways to choose 4 digits that match exactly 3 of the winning 4 digits. So the probability of winning the small prize will be 36 divided by 10,000. Now, I have students bringing a trick here. They will say, okay, since the probability of picking all the 4 digits is 1 divided by 10 to the power 4, then probability of picking the 3 digits will be 1 divided by 10 to the power 3. That is only correct if the question said, what is the probability of picking 3 digits correct? We don't have no 4th digit. So it will be 10 to the power 3 is the sample space. All the possible outcome will be 10 to the power 3. So that means all the 3 are correct. But this question, we still pick 4 digits, but only 3 are correct, 1 is incorrect. So what we want to do is to be able to calculate the incorrect section. And that's what we did here. So again, we said if exactly 3 digits are matched, then one of the 4 digits must be incorrect and the other 3 digits must be correct. So for the digit that is incorrect, we have 9 possible choices. Because if I have 10 digits, 1 have to be correct, then the remaining 9 is incorrect. That's what happened for all the 4 digits. Every time we are going to pick 1 digit correct, we take 1 out of 10, so the 9 remain incorrect. So now we have a chance, the last one which is incorrect. What is the probability of getting an incorrect from 10 digits? Only 1 will be correct. So that's why we said there are 9 possible choices for the incorrect. So as by the sum rule, we have a total of what? 36 possible ways to choose 4 digits. That is 3 of them winning 4 digits because 9, 4 times. So it will be 9 plus 9 plus 9 plus 9. So that's why we have 36 possible ways to choose 4 digits that match exactly 3 of the winning 4 digits. So here the probability then will be, the probability of winning the small prize will be 36 divided by 10,000. Because first the 3 are already correct. Only 1 is not correct. 1 that is not correct, we're going to get 9. Anytime we pick run 1 value from the 10, only 1 is correct, 9 is not correct. The second one, only 1 is correct, 9 is not correct. The third, only 1 is correct, 9. Then we had all the 4 9s, and that's what gives us 36. So, because we already know probability of getting all the 4 is 1 over 10,000. So getting only 1 incorrect, 9999 incorrect from the 4 will be 36 over 10,000. So we have another example again. Here we said there are many lotteries that award prizes to people who correctly choose a set of 6 numbers out of first n positive integers. When n is usually between 30 and 60, what is the probability that a person picks the correct 6 numbers out of 40? So there are again many lotteries that award prizes to people who correctly choose a set of 6 numbers out of first n positive integers. Here we say when n usually is between 30 to 60, what is the probability that a person picks the correct 6 numbers out of 40? So the solution here will be using a combination. So we know the total values we have is 40. And we want to pick 6. So this means the first thing we're going to do the number of ways to choose 6 numbers out of 40 will be the combination of 40 and 6. And here we already went through how to find a combination of a values or permutation. We know a combination will be the total values factorial divided by the total value minus 6, which is the one we are going to pick. So 40 minus 6 factorial times 6 factorial. And normally in our course textbook, we use the symbol NR. N will be the 40, R will be the 6. R is what we are picking out of N, which is 40. So the formula will be C equal to N factorial divided by N minus R factorial times R factorial. And that will give us the 40 factorial, 34 factorial times 6 factorial. How do we get the 34 factorial? Because it's N minus R. 40 minus 6 will give me 34. And we know a factorial of a value means we multiply the value, decrease it by 1 all the way to 1. So 40 factorial will be 40 times 39 times 38, 37 all the way to 1. Or you can say 1 times 2 times 3 times 4 all the way to 40. Same thing, 6 factorial will be 1 times 2 times 3 times 4 times 5 times 6. Then we do our division and multiplication operations. Our answer will be 3,838,380. So the answer here, we haven't finished yet. This answer here is the possible combination of picking 6 digits out of 40 digits. The possible combination will be 3,838,380. Now, if these are the total combination of 6 values out of 40 values or digits, this tells us that the 3,838,380 is our total sample space, which is the total possible outcome. Hence, the probability of picking a winning combination, it will be only 1. So it's 1 divided by 3,838,380, which will be 0.00000026. Yeah, so again, to my main point here, this is the reason why I do not play Lotto in New York City. We have exactly this type of lottery system in New York. Actually, in the whole United States, almost every state have this type of lottery, where we have a digit from 1 to 54, you pick 5, best number, you win. The probability is almost 0. So like very rare that we see people win. The worst one is the Powerball. Powerball means you need one number, which we call the Powerball number, out of the, let's say, 54 values. Then the extra possible 5 digits. So now the probability will be, I can't even, 0.000, maybe 0 up to 12 times. So again, this alone is saving enough. If we have 4 digits from 1 to 40, and they say we should pick a number, 6 numbers out of the digits, maybe 25, 36, any number, 6 digits out of from 1 to 40, then you win the lotto. The probability of winning that lotto is what we have here. So yeah, they say, can you work out the probability of winning the lotto with the biggest prize where you live? I gave an example of the mega ball or power ball. The probability, first I'll take a deep breath. The probability is almost 0. It will be 0.0000, like 10 or 12 zeros before the value. So it's almost, even this alone is even too much, almost empty. Okay, so we have another example here. They say, what is the probability that The numbers 11, 4, 17, 39, and 23 are drawn in that order from a bin with 50 balls, labeled number 1, 2, 3, 4, 5 up to 50. Here now the question said they are in order. So what is the probability that the numbers 11, 4, 17, 39, 23 are drawn in that order from a bin with 50 balls? 50 balls means we have values from 1 to 50. A, the ball selected is not returned to the bin. So the probability of A will be a little bit lesser, which means if I have 50 values, the probability of when I get the first value, the next probability will be 49, 48, 47. So it's the values, the balls are reducing. And then the B said the ball selected is returned to the bin before the next ball is selected. So A will have better probability than B because A means if I take 11, I'm not going to put 11 back no more. So the answer will be unique values. B means I can get the same value twice. But if we can remember, in my New York State, all the lotteries that we play is A. We use the A method. So very rare that you see the lottery in New York, you see the same two values in the result. It doesn't happen. Yeah. So we're going to use the product rule for each case. Now the sampling, so the first one is the ball is selected, is not returned to the bin. So that will be the method of this sampling is called a sample without replacement. We don't bring the ball back. So the probability is 1 divided by 254,251,200. How do we get this value? As we said earlier, we started the total numbers or the total balls are 50. So first we get 50. Second times, we're using the product rule. Only 49 left, so 49 times 47 times 46 times 45. Why 45? The time we are going to pick the fifth value, some of the values, the previous values that we picked, they are all gone. We don't replace it. So that will be the value we get here. 254,251,200. So this will be our total sample space. The second one, remember it to be 50 throughout. So we get 50 times 50 times 50 times 50 times 50. Because when the ball is selected, we return it back to the bin. So there's a chance that we can select 5 numbers and the same number will appear twice. So you can see the result of both now. This is why I'm saying the probability of having A is better than B because it will be 1 divided by 312 million. So the probability value will be lesser. The first one is 1 divided by 254 million. So we move to the next concept of the probability of complements and also the union of events. So the union of events means, and that's the term union. We have 2 events. So what is the probability that those 2 events will occur? Normally, if it's union, we had the 2 events together. And again, we will go through. Complement means opposite. So for example, what is the probability of A? If I have 2 events, event A, event B, and we say the probability of event A is 0.8, what is the probability of the complement of A? Complement of A means what is the probability of not A? Okay, if A is 0.8, then not A will be 1 minus 0.8, which will be 0.2. Because our first theory of probability said the total possible outcome which is the sample space, all the probabilities is 1. When you had all the probabilities of the sample space, the possible outcomes is 1. So if I have only 2 outcomes or 2 events, A and B, and probability of A is 0.6, so probability of not A will be 0.4. So let's go through the first theory. Here they said let E be an event in sample space X. The probability of the event E complement is equal to S minus E. S is always 1. That's the sample space. That's the total outcome. So if E is an event in a sample space, the probability of not E will be 1 minus E because S is always 1, which is S minus E. So the complement of the event E is given by the following symbol. Probability of not E or complement of E equal to 1 minus probability of E. So that's again the complement rule. Complement means not, opposite. So probability of B is 0.6. What is the probability of complement E? B. If B is 0.6, probability of not B or complement B will be 1 minus 0.6. Sometimes we may say complement, sometimes I may use the term not. So complement of E means not E. Complement of D means not D. So we can prove this by using the fact, here we say complement of E or not E equal to S minus E. So probability of not E is equal to S minus E divided by all the sample space, which will be S. So we get 1 minus E divided by S. And remember, E divided by S will be probability of E. So probability of not E will be 1 minus probability of E. Then probability of complements and union of events, we have the example here. So a sequence of 10 bits is chosen randomly. What is the probability that at least one of these bits is 0? So first, we need to know the sample space. Then when we know the sample space, we're going to divide 1 over the sample space to get. So a sequence of 10 bits is chosen randomly. Remember, this is bits. So that means every run, we have only 2 possible digits. Now, if it's a decimal number, as we saw in the lottery, if I want to pick 10 digits, then it will be 10 to the power 10, because every run I have 10 possible. Here we have a bit. So every run, we only have 2 possible outcomes, because a binary 0 and 1, only 2 bits. Or I'll say 2 digits, 0 and 1. So the sample space here will be 2 to the power 10, which will give us 1024. 2 to the power 10. Why? Because we are a sequence of 10 bits is chosen randomly. Each time we choose 1 bit, we have a possible of 2 outcome. So that will be our base 2. The number of bits we are choosing is 10, so it will be 2 to the power 10. Now the question is, what's the probability that at least one of these bits is 0? So here we say let E be the event that at least one of the 10 digit bits is 0. That is at least 1. So we can get 0, the next time 0, 0, the next time 0, 0, and the last will be all 10 zeros. If the most 0, then we have only 1 options. By here, the question said at least we have at least one of these bits is 0. So that means first we can have 1, 1, 1, 1, 1, 1, 10. We don't need that. There's no any 0. Now the rest of 9 different combinations, we have at least 1 0 throughout. We can get 0, the rest is 1, 2 zeros, the rest is 1, 3 0, the rest is 1, all the way till we even have all the digits zeros. But only one possible combination that we are going to get all the values 1 1 1 1 10 bits. So if we have this idea, now we are going to put it into a probability concept. So here we say let E be the event that at least one of the 10 bits is 0. Then not E is the event that all the bits are 1. And we know that not E will be only one possible combination where we have all the 10 bits 1 1 1. Now the rest we have 0 and 9 ones, 2 zeros and 7, etc. So that's why we said the size of the sample space S is 2 to the power 10. We get that one because every run we have 2 possible outcomes and we need 10 bits or 10 digits. So the probability of E should be 1 minus probability of not E. We do this, the reason why we are using this formula, because not E is only one time. Not E is just 1 over 2 to the power 10. I don't want to write the formula that, okay, we have at least 1 0, so we have up to 9. So you cannot say, okay, this is 1 over 2 to 10 times 1 over 9. No. Since we have an event not E is only one time, which is 1 over 2 to the power 10 when all the values are 1 1 1 1, then we just subtract that from 1. And our answer will be what we have here, 1023 divided by 1024. Now let E1 and E2 be events in the sample space. So here we're going to explain the concept of a union of an event. The union of event can be 2 or more. Here we are using 2. We have event 1, E1, event 2, E2. So if we have E1 and E2 to be event in the sample space S, then what's the probability that we get there? Maybe we have 20 events or 10 events. What's the probability that we can get 2 events, E1 union E2? So this will be probability of E1 plus probability of E2 minus probability of intersection of E1 and E2. Why? The best way to explain this is using the Venn diagram. You can see that we may have an event where only E1 occurs. We may have an event whereby only E2 occurs. We may also have some event that it occurs in both E1 and E2. But if I had all the E1 and I had all the E2, I may repeat some of the events that occur between E1 and E2. And that's the intersection. So probability of E1 intersect E2 means what are all the possible events that it takes place for both U and U2 is common, it takes place for common. So we need to subtract that. Now, the best way to explain this is to look at the example given here. Now, here they say, what is the probability that a positive integer selected at random from the set of positive integer not exceeding 100 is divisible by either 2 or 5? So what is the probability that a positive integer selected at random from a set of possible integers, positive integers, not exceeding 100, is divisible by either 2 or 5? What we mean here is that, first of all, it's positive integers. So I will say that my sample space there should be from 1 to 100. There's no negative value. Or you can even say 0 to 100, because 0 also is a positive value. But normally 0 is like a neutral. It can be negative. It's not negative, it's not positive. But I would say it's positive. So now, divisible, instead of only 2, if it's only 2, then we have only 1 event. But here we have 2 events, 2 or 5. Now, the key word is or, which means it can be either 2 or 5. we add them together. So this is where the union concept comes. Now, if this question said, what is the probability that a positive integer selected at random from the set of positive integers not exceeding 100 is divisible by either 2, and 5, then it will be interception. Probability of 2 intercepts 5, divisible to 2. And so always when we have our question, we should look for the word or and n. Or is union, which is plus, and then n is intersection. So what's the solution? We said let E1 be the event that the integer is divisible by 2, as we said 2 or 5. So E1, first event is 2, second event is 5. And let E2 be the event that is divisible by 5. Then the event that the integer is divisible by 2 or 5 is a union of both of them. So E1 union E2. And E1 intercept E2 is the event that it's divisible by 2 and 5. So that's why I said interception means n, which means it have to be divisible by 2 and 5, all the possible. And union means it can be only 2, it can be only 5, or it can be both. Doesn't matter. So that's why we use addition here. Now let's say a very simple example. Let's say I'm going to use a very small value. Let's say 9 or 10. Let's use 9. And we say what is the probability that 2 or 3 is divisible by 9. So we see 2 or 3. When I look 2 is 0. Nothing, 2 doesn't divide. But when I take 3, I can get 3, 9 by 3 goes in. And that will be the divisible, the answer. But now let's look at this answer. They say E, which is 2, E1, which is 2, E2, which is 5, divisible by 2 or 5. The value can go up to 100. So we say the probability of E1 plus probability of E2 minus probability of E1 intercept E2. So we want to remove where both again. But the reason why we write this formula union, again, let's go back. They say either 2 or 5. Event E1 is 2, event E2, all means union. Now, if they say 2 and 5, then we have n. If it's 2 and 5, the intersection. So here we have probability of E1, again, union E2 is probability of E1 plus probability of E2 minus probability of E1 intercept E2. We know the values, so we use 50 by 100 plus 20 by 100 minus 10 by 100, which will give us 3. If we do these arithmetic operations, we get 3 by 5. Again, why we get 50? Maybe I should explain that point. 50 by 100, why? We have to know it. 2 is an even number. We have values from 1 to 100. Only half of them will be divisible by 2. Because all the even numbers will be divisible by 2. The odd number not. So 3 divided by 2 is not divisible. We have remainder 1. 99 divided by 2 is 45 remainder, no, sorry, 44 remainder 1, or 49 remainder 1, 99, 44 remainder 1. Oh, I said 44 again. It should be 49 remainder 1. So what I'm just trying to say is that the reason why we have 50 here, because when we divide even number by 100, half of them will be divisible. We only use the even numbers. The even numbers in 100 is half of 100, so it will be 50. Now, why do we have 20 here? Because when you look at 5, only 20 values in 100 will be divisible by 5, which we will start with 5, then 10, 15, 20, 25, 30, 35, all the way to 100 by 5. So 100 divided by 5 is 20. So that's why. Then we say minus Y1 intercept Y2. And here we say is 10 over 100. This means Y1 intercept Y2 means out of the 100 values, what values that is divisible by 2 and also is divisible by 5? Not all, n. So this will be 10 is good. 10 is divisible by 2. It's also divisible by 5. But when you look from 11, aside from 10, I can't, actually, let's start from 1. We know from 1 it's not good. 4 is good for 2, but it's not good for 5. 5 is good for 5, but it's not good for 2. So you see that all the values will be the values that end with 0. When a value ends with 0 is divisible by 2, is divisible by 5. It's an even number and 5 can go in. So we're going to get 10, 20, 30, 40, 50, up to 100. And those are 10 values. So that's we have 50 over 100 plus 20 over 100 minus 10 over 100, then the arithmetic operation. One more time, Y1, the reason why it's 50 because 2, how many values from 1 to 100 is divisible by 2? It will be 2, 4, 6, 8, up to 100. So half of 100 values. So that's why it's 50. Now, why 20 here? 5. How many values are divisible by 5 from 1 to 100? It will be 5, 10, 15, 20, 25. If you count it, it will be 20. And how many values are divisible by both 2 and 5, which is the intercept? It should be 10, 20, 30, 40, 50, up to 100. And that's why we get 10. So this is our last example for these lectures. We have a question here for a Monty Hall puzzle. Monty Hall puzzle is like a TV show. We can see the diagram here. We have 3 gates here, 1, 2, 3. Back of these gates, there is prices. So if you choose the right gate, you get the price behind it. And some of them may not have anything. So if you choose, let's say 3 and there's nothing, you don't get anything. You choose 2 and there's a TV, you get TV. You choose 1, there's a cell phone, you win it. So now the question says you are asked to select one of these 3 doors to open. There is a large price size behind one of the doors. And if you select that door, you win the prize. After you select a door, the game show host opens one of the other doors, which he knows is not the winning door. The price is not behind the door, and it gives you the opportunity to switch your selection. Should we switch? Of course, yes, I will switch. If I pick 1 and the price is not there, I may pick 2, the price is there or it's not there, 3. But in this case, the host of the show pick one of these doors and the price is not there. That's the condition they give you. You are asked to select one of the 3 doors to open. There's a large price behind one of them. One of them have the highest price. And if you select that door, you win the prize. After you select a door, the game show host opens one of the other doors, which he knows is not the winning door. The price is not behind the door, and it gives you the opportunity to switch your selection. Should you switch? So yeah, this is a notorious confusing problem that has been the subject of much discussion. Do a web search to see why. I mean, decided to switch it. First of all, I haven't decided yet. And maybe I'm okay, it's 2. Then the door and the host of the show the first door there's nothing. And it said, okay, you think, should I take 2 or 3? Now the question said, we should switch or not. Now, this is the solution from this lectures here. We said you should switch. Now, the probability that your initial pick is correct is 1/3 because it's 3 doors. This is the same whether or not you switch the doors. But since the game show host always opens a door that does not have the prize, if you switch, the probability of winning will be 2/3. Now, if you switch, the probability of winning will be 2/3 because you win if your initial pick was not the correct door. And the probability your initial pick was wrong is 2/3. So again, this is a very, notice here, this is a notoriously confusing problem that has been the subject of much discussion. So I will also urge you to do a web search to see why you should switch or you should not switch your choice. So this will be our conclusion of our first lectures in probabilities. And this again, in this course, we are doing only discrete probabilities. So this course will cover discrete probabilities, and our next lectures will go more details. So again, wish everybody the best and thank you.